So, as we said that we have we can have situations where I will have ventilation controlled fire, that is oxygen is availability is not in abundance, while fuel controlled fire is where oxygen is available in plenty, but fuel is getting depleted. So, this is a situation. So, we can also do some modeling a little bit, but let us see, let us understand first physically. Model is not important, I am not going to solve the model here, but give you the physical understanding of this. So, let us say this is my combustible material and fire has started, the plume, that is burning gases, hot gases, flame, etc., put together, they actually rise and hot gases filled in this space. Hot gases will fill in this place. Hot gases will fill in this place. Hot gases will generally it will fill in these spaces. Hot gases will fill in these areas. So, the hot gas layer, it accumulates up to this line. It will accumulate up to this line first. There is only one opening left here, just for our simple understanding. So, it will accumulate up to this point, and then what will do? Once this is accumulated up to this point, it will now start going out, because hot gases, their density is less, temperature high. We will model it also, do not worry, a little bit equations you will like it, put it. So, hot gases goes out through the top, but what happens is, to sustain the fire, and there is a volume, like the gases are going out, something must come and fill in this space. The volume is conserved, volume is same, volume is the room volume is same. So, if something is going out, something must come and occupy that space. Hot gases tend to occupy it, but to generate hot gases I need oxygen to come from the bottom. So, oxygen comes from the bottom, oxygen or air comes from bottom, sustains the fire condition, and then gases accumulate, and when it becomes more, it tends to accumulate over half of the opening area or some portion of the top half of the opening, and oxygen comes from the bottom half, usually bottom half or nearby half or something like this. Plane where this, below which oxygen comes and above which the hot gases go out, we call it neutral plane, because nothing is going out, nothing is coming in there, the pressure must be 0. So, that is a neutral plane, pressure inside and outside must be 0, that is a neutral plane. So, that is actually behavior of the fire. So, external temperature is Ta, and then internal temperature goes on increasing, right. So, that is it. Now, let me define a few things before I go to standard fire. So, this is the behavior of fire in a room. I have not defined, I think, something. So, oxygen I have talked about, but related to the fuel I have not told you something. How do I quantify the fuel content in a space? Fuel content in a space, fuel content in a space, room or something like this. Well, we define in terms of what is called fire load. Now, what is fire load? Fire load is, you can identify total quantity of combustible material in the room. Total quantity of combustible material in the room divided by the area, floor area or internal surface area. People use both this, but generally it is floor area, right. So, fire load is nothing but sum total of all combustible material multiplied by their delta Hc. So, it would be actually mass, right, mass of the combustible material. So, let me put it as, shall I use capital M or small m, I do not remember what to, small m we have used for burning rate. So, let us use capital M, mass of all combustible material, MCI, let me call this ith material, into delta HCI of that material, right, or heat of combustion of that material or fuel value or whatever it is, divided by floor area. So, fire load I might talk in terms of megajoules per meter square. Megajoules per meter square. Fire load, I might talk in terms of megajoules per meter square. But something interesting is there, interesting in the sense that earlier all experiments that is done to understand the fire in furnaces, they used wood, small wood pieces. Therefore, there is another way of expressing this fire load in terms of equivalent kg of wood. So, the megajoule per meter square, if you divide it by the calorific value of wood, actually. So, the megajoules per, so this is actually calorific value of all the fuel, megajoule per meter square multiplied by calorific value of wood, which will be again in megajoules terms per kg. So, you will get kg per meter square wood equivalent, kg per meter square wood equivalent. So, kg per meter square wood equivalent, right, wood equivalent, kg per meter square wood equivalent. So, you get kg per meter square wood equivalent. So, that is how fire load can be defined, that is how fire load can be defined. So, fire load is, now it depends upon occupancy class. It depends upon occupancy class. For example, in residential building, type of fire load you will have is different than in an office, right. And in office again you can have two types of scenario. One, all papers are, today of course things are quite different, but good old days you will have lot of papers, some offices, some other offices you might have all of papers locked up in a steel almirah. So, those ones are, will have less. So, fire load is based on that. However, in occupancy class you can, in the occupancy class residential, etc., which we will talk about sometime later on, occupancy classes. So, fire load can be related to the occupancy class itself, like you do for even gravity load. Gravity load is based on occupancy class today. So, that is what it is. So, fire load is defined in this manner. Now, let me see if I have defined this fire load somewhere. Fire load not really, here I have not defined, I will see if I have defined them somewhere. Okay. So, fire load is, that is how we define fire load. Now, if I have to compare a building element, you have to compare a building element for its performance against fire. I must have some way to quantify this performance, right. And from this point of view, what it would be, for example, if it is a wall or a roof or ceiling, floor slab or the floor system, then I must be able to quantify their fire performance. Now, how do I quantify their fire performance? Well, issues I mentioned earlier. The first thing is that it should remain as it is, means should not really fail structurally. If it fails structurally, that is a disaster altogether. So, it should not fail structurally, but I also said that it should not transmit the fire to the next room. Now, how can it transmit the fire to the next room? Either the flame may go away or the heat can get transferred. Supposing heat transfer through this is very large, lot of heat can pass through it, conduction heat transfer, and that heats up the next room combustible material. Supposing 1000 degree in one room, and next room I have got, the conduction is so high that next room it goes to 200, 300, 400 and ignites there, then there is a problem. So, there is the one issue is related to the structural performance, the other issue is related to the performance related to conduction of heat, but there is a third aspect also, the flame. Now, when can flame pass through it? Supposing it develops a large crack because of differential expansion, etc., or material degrades at higher temperature, generates cracks, right, drying or similar sort of thing, whatever it is. So, if the cracks become too large, even hot gases and flame will pass to the next room. So, the performance against fire is judged by this type of three conditions. One is the structural, I will have again this in the slide. One is the structural performance, other is the insulation quality, and third is the integrity. It should remain integral. I mean, standing all right, structurally still safe, it will not collapse, but if it is not integral, there is some gap, hole has come into it, it will actually transmit a heat. So, this is the performance how we define against performance, but performance against what fire? Performance against what fire? Because the fire that will be there in a given room will depend upon the fuel condition of that room, ventilation condition of that room, right. So, it is space dependent, it is space dependent, it is not independent of the space. You cannot say that if I have residential building, all residential building will have similar kind of fire. Now, how do we define fire? We said by temperature versus time temperature curve. So, time temperature curve of all the spaces are unlikely to be same. Therefore, how do I judge these materials or elements, structural elements, beam column or slab or wall or whatever it is? Well, we have to have a standard fire. I have to have a standard fire. So, that is the concept of I need a standard fire. That is the concept of standard fire, right, concept of standard fire. Now, this actually standard fire, this concept started developing somewhere around 1920s. People started doing experiments in furnace, and largely they found the typical, most of the typical fire would go around 1000 degree, 1200 degrees centigrade in about an hour and 1.5 hours time, and then try to come out with a standard fire which will cover almost all fire, effect of all fire, cover almost effect of all fire. So, if you see actual fires would look something like this, because we said that if I look at the post flashover situation particularly, because before that it is in some corner, I am not so much worried, it will build up, be a steady position, then it depletes and temperature would be somewhere there. Now, the other fires also, I have some more diagram of fires, I will see that, we will see that how they behave. Generally, you will find it something like this. So, they deplete after certain period of time during beyond fire, duration of fire. Now, standard fire was basically arrived at by consensus of people, like you have loads. If you look at the loads loads that you take in buildings, of course, the bridges things could be different, because they are more or less the vehicle. Bridges or depend many other industrial structures specific but then you have impact factor, etc. You can estimate specific cases industrial, it becomes complex. But bridges, for example, class A loading, etc., etc. There are other kind of loading, class A loading, etc. Tank in so whatever it is. There relatively it is more or less the load is somewhat known, the extremities of the load. But when it comes to building, you have characteristic loads which has been arrived at by consensus, because it is very difficult to measure the load of all the furnitures which are quasi static load actually. Dead load is continuous, it is a steady load, it will be there all the time, but imposed load is actually quasi static. I mean, supposing somebody wants to change the furniture of a classroom tomorrow and it becomes lightweight, the load actually changes, or it becomes heavy because you have put in some kind of teaching equipments, let us say, it changes the culture. So, they are quasi static usually, number of people come in and go. So, it is very difficult to come out from a measurements of 5% load that will be exceeded only 5% of the time, the characteristic load is exceeded only 5%. So, people have arrived at that by consensus, experts, consensus all over the world. Some measurements were also done somewhere. Similarly, in case of fire, the standard fire was arrived at by kind of a consensus of experts, STM standard fire or Indian standard fire, this is basically adopted from appropriate international code, and that fire is something like this, ASTM time temperature curve. So, what they do is this monotonically increases, it does not stop, So, as the time passes, the temperature is higher than the real fire. The concept is like this: the severity of the effect of fire, if you see on human being, fatality, you can sustain 30-40 degrees centigrade for very long time. You put somebody in a chamber 100 degrees centigrade, the time would get reduced. 250 degrees centigrade could be very fatal in a very short time. Some tissues will simply be damaged. So, there are so the time is important. I mean, why I mentioned this point is temperature and time is important. If you see the materials also, since the material is not very for example, I was talking about that wood thing. If you cut pieces of wood, spread, that is important. That is why per unit area, fire load per unit area is important, density. See, if you have pieces of wood, that would burn faster, that would catch fire at various surface areas large. While I have a log, it does not burn the same. So, if you see, the effect of fire depends upon the fuel density or load density, right. So, the area is important, area or the distribution of this is actually important. Now, what I was just mentioning is that time and temperature issues actually. So, basically if I take the material, any material, if I expose it for a longer period of time at a same temperature. Now, point that I was why the wood thing came actually. If I have a thick log, heat has to pass from outside periphery to inside. So, it will take longer time for heat to pass into. Now, if you see our structural elements, they are not thin elements, they can be thicker elements. So, if you have longer time, then even inside material will get affected, while surface might get affected initially. So, time is also an important factor. It is not only the temperature. Supposing somewhere the temperature goes high up, but then it quickly comes down, the heat will not be able to pass into the structural elements inside, or for that matter any other thing inside, it will not be able to pass. So, time is an important, so effect of the structure, because most of the material would degrade when exposed to higher temperature, whether steel, concrete, plastics of course is much faster. If it is a thermoplastic, glass transition softening point, glass transition temperature could be 70-80 degrees centigrade. Now, therefore, time for which it is exposed, that is also an important issue. So, what has been thought is two things, time as well as temperature. Now, how do you take care of this? That would be one of the simple way would be integrate area under this curve. That takes care, like it is area under this curve would be, supposing I consider temperature T and small time dt, I want to take effect of both. So, the just integrate it over the time 0 to whatever time you like. So, basically the area under the curve is important, because where I have larger area under the curve, that is slightly smaller temperature for longer period of time, right, slightly smaller temperature, but for longer period of time, that will be equivalent to slightly higher temperature for absolutely. So, that is why what was done is standard fire is monotonically increasing. Actually, this fire is above, many of the actual fire could be above, not necessarily all would be above, but many of them could be above, but even then by consensus people have arrived at this kind of thing. So, this is ASTM time temperature curve, right, this diagram showing, but if you see the Indian, I superimpose over it, this is given Indian or British or many other actually internationally, this is also STM same curve. T is equals to temperature, the standard time temperature curve, which I need. Why do I need? Because I have to judge the performance of element against a standard fire. Fire from room to room varies, but if I have to say this wall is better than that wall, then I need a standardization of the load or fire to which I should subject it to. So, that is why I need a standard fire. So, standard fire was arrived at by people from initial experiments and then consensus of experts, and one of them which is used for this kind of fire, not fire associated with let us say petrol pump, inflammable liquid, where the temperature will go up very fast. So, forget that, but this occupancies of the kind of residential office etc., standard time temperature curve for fire would be given by this expression, where this stands for ambient temperature at 0 time before fire, plus T is in minutes. T is in minutes. So, 8 T plus 1, log 8 T plus 1. Obviously, I have to have 1, otherwise log 0 is not defined, right. So, supposing it is 1 hour, how much will be this temperature? This will be 60 minutes. So, 8 into 60 is 480, 481, this value is 481, 1 really does not make any difference. So, take log of 481, right, log of 481 will be 2 point something, 2.68 multiplied by 345, 925 plus 25 degree or 30 degree centigrade ambient temperature. So, let us say, so it will come to around 1000, close to 1900 and something. So, you see this is the standard time temperature curve. Now, this is used to define fire resistance. This is used to define fire resistance. This is used to. So, if you it is not only in fact in we were surveying just to again deviate from this a little bit. We are surveying one of our student was working on, I am still working on failures of bridges. Look at failures of bridges, he surveyed whatever is available in net and things like that, and one of the causes he found that a number of bridges collapsed because of fire. Then he found that out of 6-7 causes, fire was also one of the causes for some failure of some of those bridges. So, but in any case, the point that I am trying to, because they are from transportation engineering, if somebody is from transportation engineering, these issues are relevant there also. Maybe you do not look at the fire resistance exactly in the same manner you do for building, because bridges are in open. So, this is fire resistance we will define with respect to standard fire. So, let us see how do we define further, right. So, a structure should be able to withstand standard fire, that is how we define, for a specified time. Hence, fire resistance is defined in terms of time. So, unit of fire resistance is seconds, minutes or hours, generally hours. So, people will talk in terms of 1 hour fire resistance wall or 3 hours fire resistance wall or 4 hours fire resistance wall and things like that. So, fire resistance is talked in terms of its unit is time up to which it will sustain the standard fire, right. Now, how will you sustain performance? Collapse is one issue, as I said, but spread of fire is an equally important issue. So, fire resistance in time during which the element can endure the standard fire in terms of stability, integrity and insulation. Stability, integrity and insulation, all three, and it is not or. It must be able to sustain. That means failure is or. That means failure is it fails by this or that, whichever fails early. So, if the insulation is broken down earlier, then still the fire resistance will be that much time, or integrity is lost by that much, so it will be related to that, right. Okay. Now, how do I judge stability? That is very easy, because for civil engineers to understand how do I judge stability, it is very easy for civil engineers to understand that, because failure is in terms of either collapse or excessive deflection. Excessive deflection here, one of the major serviceability limit, excessive deflection. So, if the deflection becomes high, that would actually lead to imminent collapse later on. I mean, if the material has got a lot of deformation capability, then ductility it has got a lot of it, the system it can deform before failure, then it will give indication, but anyway after beyond a point it is not acceptable, it might go to the plastic zone. So, therefore, stability is defined as normally done for a slab, for example, it is related to the span or a beam, it is maximum deflection is related to the span or the span depth, etc. So, it is related to that. So, therefore, it is related to that criteria, the deflection or collapse. Insulation is defined in terms of temperature rise on the cold side. Now, what you do is actually you have furnaces where you subject such elements, whatever the elements is. If it is a linear element like beam or column, linear element. Put it in the same manner as you expect the load supporting system as well, because behavior will depend upon the structural behavior depends upon the fixity at the end and things like that. Now, wall etc., wall or floors or ceiling, roof, whatever it is, those kind of horizontal system, two dimensional system, 2D elements, actually linear elements or 2D elements. So, 2D elements, the subject, for example, if it is a wall, they will heat up this portion. If it is a wall, they will supposing this is a wall. Oh, the color is not changing. This is a wall. So, subject this specimen to heating on this side, maintain the temperature. I mean, this will not be like this, actually it will be through heating element, maintaining the temperature. It is a total temperature controlled, right, and this is the cold side, So, you have to have lot of temperature measuring devices, that is thermocouples on the cold side, and temperature rise you have to monitor. So, in India we have facility in CBRI, there may be one or two more, maybe one or two defense laboratories they have, but the best facility of course is available in CBRI. There are a couple of institutions which are trying a little bit. One I think is there's some facilities, something structural fire testing, a little bit of facility in Mysuru, National Institute of Engineering, NIE. They have a small facility they have set up. Some other places also they are trying to set up similar sort of facility, but CBRI has got the full best facility, and this temperature here on the furnace side is totally controlled. You have a control room, computer control system. So, you have to see that it maintains the same time temperature, T equals to T0, T equals to T0 plus 345 log 80 plus 1. So, this you need a controller, so it's controlled system. So, temperature cold side you measure, hot side obviously you will have thermocouples, and gas temperature you will be continuously measuring gas temperature, because that is how it is defined. It is in terms of gas temperature, not the surface temperature. Surface temperature is also measured, and then you will have strain gauges or any kind of modern days there are cameras, digital, you can measure them through various kind of other kind of advanced techniques of deformation measurement. So, you have to have deformation, may not be strain, but at least deformation measurement, some sort of deflection, and because deflection criteria is important, strain may not be, but deformation criteria. So, deformation measurement devices has to be there. And then the third thing is integrity. Now, how do you measure integrity? Integrity is measured by very innovative way they actually propose by the experts, right. They proposed very innovative way. It is like this: if there is a crack seen here, you continuously observe on this side, on the cold side, is there a crack? Now, if you find a crack is developed, then you put a standard cotton pad in front of the crack. Now, if it catches fire within a specified period of time, if this cotton pad catches fire, you bring a cotton pad, and if it catches fire within specified period of time, you say integrity is lost. So, three measures: one, deformation, collapse anyway you can see, but before that you will be seeing deformation. Other thing is measuring the temperature. Third thing is measuring the integrity through this cotton pad measurements, and whichever fail first you stop the experiment. That is the fire resistance, right, that is the fire resistance. Okay. So, that is how fire resistance, we will define more of it. If you have some question, I will like to answer.